Alright, so here we go, lesson 2-5, piecewise functions. We're going to start off with a warm-up, and we're going to graph f of x equals negative x plus 6. This is just a linear equation, but we're going to graph it where x is less than 1. So there's a couple of different ways you can do these. You could just graph the whole line and then erase everything back to 1. But basically, if I'm going to start at 1, now you notice it doesn't say equal, but we'll talk about that. I'm just going to go ahead and plug in 1 to the function. So this is going to be negative 1 plus 6, which is going to give me positive 5. So when x is equal to 1, y is equal to 1, 2, 3, 4, 5. But because it says x less than 1, I'm going to use an open circle. All right, so I'm not going to put a full dot there. I'm just going to do an open circle. And from there, I can use the slope of this function to help me finish up. Now this is a negative slope, so that would be normally a down 1 over 1, but I want to go to the left, so I'm going to go up 1, left 1, and I'm going to draw my function that direction. So that's the graph with a restriction of x less than 1. My second one is g of x equals 2, and my domain is only the number 1. So what this means is you have a single point, 1, 2. That's it. That's all you get right there. Okay? My last one is a parabola, x squared plus 1. We just got done talking about how to graph these. And the domain here is x greater than 1. Now here's the tricky part about this. A lot of us might know how to graph this parabola, but when we start to restrict the domain, it's going to get a little trickier. So maybe what I want to do in this case is just graph as though I was going to graph the whole thing. So my vertex is there at 0, 1. My pattern of points would say up 1 over 1, up 1, 2, 3 over 1. Now obviously I don't need to do the left side because it says x greater than 1, and so I can erase now my point at 0, even though I did graph it, that's okay. I can erase this at 0, and then my point at 1 should actually be an open circle. So I can still use that same pattern of points to graph these, and I would end up with a parabola doing something like that. Just make sure you don't graph it as a straight line. So when we talk about piecewise functions, a piecewise function is a function that's defined on a sequence of intervals. Okay? On a sequence of intervals. For instance, this first graph of f of x equals negative x plus 6, that was defined on the interval from negative infinity to 1. My second graph was defined on the interval from 1 to 1. Seems kind of weird, doesn't it? And then my last graph was defined on the interval from 1 to infinity. So that's what we mean when we talk about a piecewise function. So now, if you look at what we did in the warm-up and what I have written on the left side here, and I do need to make one correction. This piece here should actually say x squared plus 1. Right? If you look at what I have written here, I have written the exact same thing that I had in the warm-up, but this is how we write a piecewise function. We don't graph 3 different pieces on 3 different graphs. We're going to graph all 3 functions together on the same graph. So basically what I'm going to do at this point is, what I'm going to do is I'm going to just simply copy what I did up top here. So my first point was at 0, 1, 2, 3, 4, 5, with a slope going that direction. My second point was the point 1, 2. So you'll notice the reason this is a function is because the top point is closed, the bottom point's open, so I still pass my vertical line test. And my third function actually started at 1, 2, and then it went up 3 and over 1. So I do have this function that looks like this, and each of those 3 parts does fit the intervals or the restrictions. Okay, so these guys over here, these guys on the right side, these guys are the intervals or the restrictions for the graph. Okay, and just a little calculus precursor. Is this function continuous or discontinuous? A function is only continuous if you never have to pick up your pencil to draw it. And I don't have that option here. I would have to draw this first line and then pick up my pencil and draw the second part. So this function is discontinuous, all right? Discontinuous because you have to pick up your pencil to draw it. You have to pick up your pencil to draw the entire graph. Okay? So when we talk about continuous or discontinuous, continuous means that all the pieces are attached. All right? Let's take a look at our next one here. It says graph the function. And again, just like the warm-up, I'm given 3 different pieces here. And I want to graph each piece, ignoring the other pieces just for the moment. So I'm going to graph, this first one here is like graphing y equals the absolute value of x minus 3. And I'm only going to graph it when x is less than 0. So again, you might need to start out by graphing more of this and then erasing the parts. So the absolute value of x minus 3, that's a shift to the right 3 units. Okay, so I would start off with a vertex at 3, 0. This has a slope of 1 to 1, so I would continue to graph 1 to 1. And you'll notice that I'm graphing way over to the left side. And the reason I'm doing that is because I need x less than 0. So when I actually got to x equals 0, I should have put an open circle there. And then I'm going to come back and erase these guys that are on this side. Now, once you get a little better about this, they're a lot easier to do, but that's the first piece of that graph right there. Okay, and I'm going to do this one in different colors just to make each piece stick out. My second part is just the line y equals 2x plus 3. Okay, so now keep in mind that I'm going from 0 to 2. So I don't need anything on the negative side. I'm going to start with my y-intercept at 3. I'm going to use my slope to go up 2 and over 1. And up 2 and over 1 again. But I'm not going to do it a third time because I'm already at the point where x is equal to 2. So this piece of the graph goes between those 3 points right there. My third piece is the graph of y equals negative x. So if y is equal to negative x, that would normally be something that starts here at 0, 0, has a slope of negative 1, comes down like this, and again, you'll notice I'm only going to the right side because it says where x is greater than 2. There's no equal sign on the 2. So that point that I had at 2 should be an open circle again. And I would draw my graph just like that. This graph is discontinuous for the same reason that the first one was. Okay? So some general things you want to keep in mind is when do I use open and close points? Open points get used for less than or greater than. Close points get used for equal signs, so less than or equal, greater than or equal. Are your arrows going in the proper direction? You'll notice on the graph above in example 2, I have an arrow on the left side of the blue one, but not on the right. I have no arrows in the middle piece, and I have an arrow on the right side of the gray one. So we just want to keep in mind whether something is a line segment versus a full line, or versus a ray, or even a point. Okay? Number 3, I would encourage you at this point to turn off the video. Try this on your own. See what you can do. Okay? And here we go. I'm doing the negative square root of x. Now this is a tricky one because the square root of x is normally just a graph that rolls out like that. If I put a negative inside there, it reflects it over the y-axis. Now there's nothing else going on here. There's no shifts, there's no stretches, there's nothing like that. So what I want to do is I'm just going to graph this with a reflection over the y-axis. Okay, so that's what my graph would normally look like, but I'm supposed to start when x is less than -1. So there's two things going on here. Number one, I don't need to point at 0, 0. And number two, my point at 1, 1, that should be an open circle. So I'm going to roll up and to the left with an arrow on the left side. There's my first piece. My second graph is y equals -x, and it's going from -1 all the way up to +3. So again, I can start this graph at the origin, which I will do. I'm going to go up 1 and over 1 to the left because I need a negative slope, so I'm going to be filling in that point. And I need to continue the slope all the way until x is 3, so down 1 over 1, that's x equals 1. Down 1 over 1, that's x equals 2. Down 1 over 1, there's x equals 3. And that should have been an open circle there because I'm less than 3. So this turns out to be a line segment between x equals -1 and x equals 3. My last one is a parabola. So let's switch colors here again. We'll see what we can do here. Now I'm graphing a parabola that has a vertex at 2, -4. So the first thing I'm going to do is I'm just going to put that on the graph. So 1, 2, and 1, 2, 3. So that parabola would normally be starting right there. There's no shift, or excuse me, there's no stretch, no reflect. So this is a normal parabola, and I'm supposed to graph from x greater than or equal to 3. Well, normally this parabola would go up 1 over 1, so I'm going to fill in that gap, and then it's going to go up 3 and over 1. If you really wanted to, you could do the next one, which by the way is up 5, 1, 2, 3, 4, 5, and over 1. So you could do that, but I'm just going to ignore that very first point, and I'm going to erase this guy over here. You don't want to leave extra stuff on a piecewise function. And this guy is continuous because I would not have to pick up my pencil in order to draw it. The question here says, what is f of 2? Now there's two ways I could look at this. I could go back and look at the 3 restrictions here. Where does 2 fit in there? It fits in the middle one right here. So I could simply plug in 2 for x, and I know that it's -2. Or I could come over to my graph, and I could say, okay, x is equal to 2 right here. What's the y value down there? It's -2. So f of 2 is equal to -2. Right? All right, let's keep moving on here. So this function here is more or less just to kind of show you that there's some interesting functions out there. This one is called a floor function, and I'm going to talk about this with the ceiling function. The floor function has these little bars that come down and they will kind of wrap underneath the x, and the floor function is defined, and the definition's weird, I always think. The floor function is defined as the largest integer less than or equal to x. Okay, so that sounds kind of funky, but basically what it means is, it means if I plug in a number for x, and I'm just going to do the first one. So if I'm going to do f of 1.2, okay, if I'm going to do f of 1.2, then I'm going to plug in 1.2 for x, and what this is going to say is, take the next integer that's lower than 1.2, the next full integer that's lower than 1.2. Well, what's the next full number down from 1.2? It's 1. That's what a floor function is. If I look at 1.5, what's the next integer down from 1.5? It's 1 again. If I look at the number 1, guess what? You don't go down from 1. We're already at the integer right there, so it stays as 1. So I'm going to graph these 3 points just to kind of show you what this looks like. So at 1.2, I'm at 1. At 1.5, I'm at 1. Oops. And at 1, I'm at 1. All right? So, but guess what? If I were to do 0, f of 0 would equal 0. So that point would actually be down here. Now, Why do I go over that? Because if I were to continue plugging in 1.3 and 1.4 and 1.9 and all that, I would basically fill in this entire gap across here, except I would have an open circle at the left side there. If I start with f of 2, you don't go down when you're at a full integer, that's 2. So f of 2 is 2. F of 2 is 2. F of 2.4 is 2. Oops, you know what? I just realized I graphed some points incorrectly here, so I'm going to have to back up. I'm going to regraph these. I went to the wrong side. 1.2 is here. F of 1 is here. I apologize, guys. F of 1, F of 1.5. So actually, my open circle that I did there, it goes this direction. Sorry about that. I knew something was looking wrong here. So the open circle is actually on that side, because when I get to 2, then my graph jumps to 2. So f of 2 is 2, f of 2.4 is 2, f of 2.7 is 2. So what happens is I end up filling in this gap again, going this way. But when I get to 3, f of 3 would be 3, which means I need an open circle here. All right? Now, if you were to continue along, f of 3.1 is 3, f of 3.2 is 3, f of 3.7 is 3, and you would go all the way across. But then when you get to 4, f of 4 is 4, and so you need an open circle here. And if you continue that, you get a series of little segments that look like this. All right? This is called a step function. You can see why it steps up as you go. Even if you go into negative values, f of -1 in a step function, you never go to the next integer below if your number that you're plugging in is an integer. So if I do f of -1, that's -1. F of -1 is -1. But let's take a look at some of these others. What if it was f of -1.2? I need to go down from there. That's -2. F of -1.4. I need to go down from there. That's -2. F of -2 is -2. So check it out. F of -1.2 is -2. F of -1.4 is -2. F of -2 is -2. But I have an open circle on this side, just like I did on the steps above. Now, if I continue filling in this graph, it would look like this. So again, it's called a step function for a reason. It steps up as you go. All right? Now, the other type of function is a ceiling function. A ceiling function does exactly the opposite. Instead of taking a number smaller than the number you're given, we go to the next highest integer. So for instance, f of, I'm just going to start at, I'll start at -1. F of -1 equals -1. F of, let's see, so let's actually plot that. F of -0.5, I go to the next integer up, which would actually be 0 this time. F of -0.1, that would be to 0, because I'm going to go up, so I'm going to go here and here, and when I get to f of 0, I'm actually at 0. So this time, the step is going this direction with the open circle on the left. If I continue on, f of 0.1, I'm going to go up, that's 1. F of 0.7, I'm going to go up, that's 1. So f1 here, 1 here. Guess what? When I get to f of 1, it's still equal to 1. On a step function, you never take an integer and go down or up from there. So then in this case, all of the open circles on a ceiling function, all the open circles are on the left side because I'm taking the higher value integer. Okay, so that's just something you can see. You may see that later on somewhere as well. All right, so the use of a piecewise function in sort of a, what I like to call a real life example here. It says the doctor's fee is based on the length of time he sees you. Up to 6 minutes costs $50. Over 6 minutes to 15 minutes. Notice it says over 6. Okay. To 15 minutes costs 80. Over 15 costs $80 plus $5 per minute above 15 minutes. All right. It says to write a piecewise function to represent the doctor's fees. All right. So what I'm going to do is I'm just going to call this f of, since we're talking about minutes here, let's use the letter m. F of m. This is a function of m. All right. Now think about this. Up to 6 minutes. Well, a doctor's not going to see you for a negative amount of time. So we would actually say, for my first one, my fee is $50. It's just a flat 50. And that fee goes from 0 up to 6 minutes. Now we're talking about the number of minutes you see the doctor. 6 minutes is included, but the doctor's not going to see you for 0 minutes. Okay, so there's my fee, $50 from 0 to 6. From 6 to 15, it's going to cost me $80. So this one's pretty straightforward, $80. 6 in my M, in my 15. Now this time the 6 is not included. The 15 is included. All right, pretty straightforward. Now over 15 minutes costs $80 plus $5 per minute above 15 minutes. All right, so we got to think about how to write this. So it's $80 flat fee, okay? And so let's see here. How would we write this? This is going to be an interesting one because I'm just trying to think if I can do this without doing anything special here. Because our minutes go above 15 minutes. All right, so I need to start off with the 80. Now a lot of people might just want to say 80 plus 5 times m, but that wouldn't really be right, because if I went for 1 minute, if you think about this, if I did this, if I went for 1 minute, I wouldn't pay the doctor $85. I would pay the doctor only $50. So what I need to be able to do is I need to be able to say it's $5 per minute for everything above 15. So what I need to be able to do here is I need to be able to take my M and subtract out the first 15 minutes, which means I'm only going to pay that extra 5 if I get to 16 minutes. So 16 minus 15 would be 1 minute. So if I go to 16 minutes, then I'm going to pay $85. My restriction here would be M greater than 15, and this would be my piecewise function. Now the last couple of questions are just basically using the function. So if you saw the doctor for 12 minutes, what is the fee? Okay, so if I'm going to go to the doctor for 12 minutes, I'm going to be looking at this fee right here in the middle. So this would be $80. If you saw the doctor for 28 minutes, what's the fee? All right, so again, 28 minutes falls into the last category. So this time I would plug in f of 28 equals 80 plus 5 times 28 minus 15. Now again, why did I minus the 15? Because I've already paid for the 15 minutes, and that second function at $80. So if you do the math here, this is 80 plus 5. 28 minus 15 is 13. 5 times 13 is 65. So your bill here would be $145. Okay? That wasn't so bad, was it? All right, that's it.